I want to start with a question that sounds absolutely ridiculous. It's a question that Einstein used to ask his friends while walking home from the university, and it drove them crazy. He would point up at the night sky and say, "Do you really believe the moon is there only when you look at it?" Now, your common sense, that wonderful tool that helps you survive in the jungle, screams, "Yes, of course it's there. The moon doesn't care if I'm watching it. The world is solid, it's real, and it's independent of me." And in our everyday life, you are absolutely right. If you close your eyes, your coffee cup doesn't vanish. If you leave a room, the furniture doesn't start dancing on the ceiling. But, and this is a terrifying but, when we leave the world of coffee cups and moons, and we dive down into the basement of reality, down to the world of atoms, electrons, and photons, common sense doesn't just fail, it commits suicide. Down there, the rules of the game change so drastically that it starts to look less like physics and more like magic. In the quantum realm, things don't seem to have a definite existence until they are forced to decide where they are. And the thing that forces them to decide, it seems to be us, the observer. I'm Richard Feynman, and today we are going to explore the single most disturbing experiment in the history of science. It's called the Double Slit Experiment. And by the end of this journey, you might not look at your own reflection in the mirror the same way again, because we are going to find out if reality is a solid stage, or if it's just a performance waiting for an audience. To understand why this is so strange, we first have to understand how the world should work. We have to talk about two things: particles and waves. Imagine I have a rusty old machine gun, and in front of me there is a steel plate with two vertical slits cut into it, slit A and slit B. Behind that plate is a back wall made of wood. Now suppose I start firing bullets at this plate. I'm not aiming carefully, I'm just spraying bullets like a madman. Some bullets will hit the steel and bounce off, but some will pass through slit A and some will pass through slit B. If you go to the back wall later and look at the pattern, what do you see? It's simple. You see two piles of bullet holes, one pile behind slit A and one pile behind slit B. This is how particles behave. They are lumps of matter. They go through one door or the other. They travel in straight lines. This is the world we know. Now let's change the scene. Imagine we are at a beautiful, calm lake. Instead of a machine gun, I have a machine that taps the water to make ripples, waves. And I have a barrier with those same two slits. When a wave hits the barrier, it squeezes through both slits. But something interesting happens on the other side. The wave that comes out of slit A starts to spread out, and the wave from slit B spreads out too. And then they crash into each other. Where the crest of one wave meets the crest of another, they combine to make a bigger wave. That's constructive interference, but where the crest of one wave meets the trough of another, they cancel each other out. They flatten the water. That's destructive interference. If you put a detector at the back, you wouldn't see two piles, you would see a complex pattern of bright stripes and dark stripes. An interference pattern. This is the fingerprint of a wave. So keep this in your head. Bullets make two piles. Waves make an interference pattern. Okay? Now let's break the universe. We take our machine gun and we shrink it down. Way down. We shrink it until it fires tiny subatomic particles. Let's use electrons. Now, an electron is a particle, right? It has mass. You can count them: 1 electron, 2 electrons. If you put it on a scale, it weighs something. It's a tiny bullet. So if we fire these tiny bullets at our two slits, we expect to see two piles of electrons on the back wall. Common sense. So we start the experiment. Click, click, click. We fire them one by one. We don't want them bumping into each other. Just one lonely electron traveling through the dark. We wait for an hour. We let thousands of these little guys hit the back screen. And then we turn on the lights to see the result. What do we see? Do we see two piles? No. We see stripes. We see an interference pattern. Wait a minute. Stop everything. This is impossible. An interference pattern is what waves do. It happens when a wave goes through both slits, splits in half, and interferes with itself. But we fired particles, and we fired them one by one. This implies something absolutely preposterous. It implies that the single electron left the gun, went near the wall, turned into a ghostly wave of probability, went through slit A and slit B at the exact same time, interfered with itself on the other side, and then decided to land on the back screen as a single particle. How can a single object be in two places at once? How can it pass through two doors simultaneously? Does the electron know the other slit is open? Does it smell the room? Physics was in crisis. The universe was misbehaving. So the scientists said, "Okay, you little tricksters, we're going to catch you." And that's when they decided to peek. The scientists were clever. They said, "We're going to put a tiny sensor, a detector, right next to the slits. This detector will tell us 100% which hole the electron actually went through. No more guessing. We are going to watch them." So they set up the detector. They turn it on. The machine gun starts firing again. Click, click, click. The detector works perfectly. It goes beep for slit A, beep for slit B. We catch every single electron. We know exactly where they went. We stripped away the mystery. But then, we look at the back wall, and the blood drains from our faces. The interference pattern is gone, vanished. Instead, we see two boring, simple piles. Just like the machine gun bullets. Think about what this means. This is the part that keeps physicists awake at night. When we didn't look, the electron acted like a wave of infinite potential, exploring all paths at once. But the moment we looked, the moment we gathered information about its path, it stopped dancing. It snapped back into being a solid, boring particle. It's as if the electron knew it was being watched. It's as if nature said, "Oh, you're looking? Fine. I'll behave like a solid object. But when you turn your back, I'm going to dissolve into a cloud of probability." This is the observer effect. The act of measurement affects reality. You cannot observe the universe without changing it. Now, don't get me wrong. This doesn't mean that your consciousness uses telepathy to push the electron around. It's not magic in that sense. It's about information. Quantum mechanics suggests that the universe exists as a wave of possibilities, what we call a wave function. And this wave function contains every possible outcome. The electron is here, it's there, it's everywhere. But when you interact with it, when you force it to give up its secrets, the wave function collapses. The universe has to choose. It has to render a single reality for you to see. Some physicists, like Hugh Everett, suggested that the wave function never collapses. He said that every time an electron has to make a choice, the universe splits. In one universe, it went left. In another, it went right. This is the many worlds interpretation. Millions of parallel realities branching off every microsecond. Others think this points to something even stranger. Think about a video game. In a video game, the computer doesn't render the entire world at once. That would waste processing power. It only renders the room you're standing in. It only renders what you are looking at. Behind you, there is nothing but code. Is our universe doing the same thing? Does reality only render itself when a conscious observer demands to see it? It's a disturbing thought. It implies that we are not just passive spectators sitting in a theater watching the universe happen. We are part of the projector. Our interaction with the world is what gives it form. We started with Einstein's question, is the moon there when you don't look? Quantum mechanics gives us a very shy, very hesitant answer. It says, maybe. It says that the solid, dependable world we think we live in is actually a shimmering ocean of probability. It says that at the very bottom of reality, matter isn't made of stuff. It's made of possibilities waiting to happen. We used to think the universe was a machine, ticking away like a clock whether we were here or not. Now we are realizing it's more like a conversation. We ask a question, and nature gives an answer. But the answer depends on how we ask the question. So, the next time you are alone in a room and you turn off the lights, ask yourself, is the room still there? Or is it just a wave of potential, waiting for you to open your eyes and create it all over again? The universe is stranger than you think, and that is what makes it so wonderful. I'm Richard Feynman. Keep looking at the stars, and maybe, just maybe, they are looking back at you. This is Physics is Not What You Think.